comes instead of virial expansion. Let's understand what comes instead of virial expansion. How can we proceed? What can we do instead of virial expansion? We can do the following simple estimate. So let's consider a probe volume in our Coulomb system. You will ask me what is the significance of this big R, and I will tell you that I will change big R step by step. I will increase it and see what happens. So at some intermediate, at some, let's say, small volume, I can say, I can count how many particles are in this test volume. So the number of positive particles will be concentration times R cubed. And by the way, concentration of positives and concentration of negatives is the same, because otherwise we would supply France with electricity for 100 years. And unfortunately, we cannot. Okay, so the number of average expected number of positives and negatives is the same. It's proportional to volume of this test sphere. And now let's make an assumption, which we'll check whether it's a reasonable assumption or not. Let's make assumption that these guys are moving independently. They don't think about each other. They just move independently. And if they move independently, then on average, the number of plus and minuses will be the same. But in every instant, like when you throw a coin, there are, I don't know English word for two sides of the coin. Yeah, always. Okay, whatever. You know what I'm talking about. So, and also probably French coin has some other names of the sides. So anyway, you have some difference between them. And the difference between them is roughly proportional to square root of the number, right? So the number is either this or that, and therefore the charge, there is either positive charge or negative charge, depending on chance. And this charge imbalance goes like square root of this number of particles. Okay, so if there is charge imbalance, then there is electrostatic energy. Because if it's predominantly positive, they predominantly repel. If predominantly negative, they predominantly repel. So there is energy, which is square of charge, Bjorn length divided by the size of this thing on this order of magnitude. So you see that square of this charge will give you R cubed divided by R. So this is like this. Okay, so this is the price of the fact, electrostatic price, energetic price of the fact that they move independently and collect some charge imbalance over this volume. Okay, so if this charge imbalance is smaller than kT, they don't care. If this charge imbalance is larger than kT, then they say, no, we cannot go there. So, and you see that the charge imbalance depends on this, on how big the size of this thing that I take. So if this size, the probe volume, is smaller than peculiar distance, which is called the bi-screening length, and you just mentioned already screening. So if this is smaller than this quantity, then indeed our assumption that they move independently is okay, is fine, and they do move independently. And on this length scale, there are fluctuations of charge. On the length scale smaller than the bi-screening length, there is fluctuation of charge. Fine. On larger length scale, fluctuation of charge is strictly prohibited. No way. On larger length scale than the bi-screening length, you maintain electroneutrality. So order of magnitude of this, the bi-screening length, if it's millimolar, 10 millimolar, it's 1 millimolar solution, it's 10 nanometers, so such that you may want to remember. Now this, the bi-screening length in general, if you have different ion components with different charges, this is definition of ionic strength. Let me skip all of this. And basically for simple one-to-one salt, ionic strength and concentration of salt is the same thing. So and there is 8 pi, okay. So now free energy. Remember, this is all to replace our familiar friend, virial expansion, square concentration, blah, blah, blah. How do we estimate free energy here? So free energy here, contribution of Coulomb interactions to free energy is actually negative. Because these guys are clever, they arrange themselves in comfortable way. When they live in free society, they can move however they want, and they enjoy this freedom to lower their free energy. So this is why this correlation, free energy as it is called, it's negative. It corresponds to more favorable arrangement of charges than random. And this is roughly 1 kT per debye blob, per debye volume. The word debye blob I don't think is very widely used, but we can call it debye blob since we are in blob land. Okay, so first of all, it's negative. Second of all, returning to the comparison of this to the virial expansion. Remember, virial expansion, you have it's just expansion in powers of concentration. So the first non-trivial term is proportional to square of concentration, pair collisions. Here, if you remember the fact that the bi-screening length, and I should have written it here too, the bi-screening length is, or this is the best formula. The bi-screening length is inversely proportional to square root of concentration. So you plug it in here in concentration to -1/2, and you discover that this is concentration to the 3/2. So it's non-analytic dependence on concentration. And the power is smaller than 2, which indicates that it's not pair contact. You cannot talk about individual contacts or anything like this. It is emergent new property, collective emergent new property. Okay, any questions? You guys are saturated in the first lecture, but I will try to wake you up. Okay, so there were coefficients like 8 pi here, 12 pi here. How do people know this? People know this by doing proper calculation, which is actually a mean field calculation. And here is a reminder of several mean fields that you already encountered in this summer school. There was Flory-Hagen's mean field theory of polymer concentration. Tube, Tom McLeish explained as mean field of other chains. Percolation on butter tree, Michael Rubinstein explained that this was a mean field treatment. And this morning, I introduced, instead of going for coffee, I introduced this line here about Frederick Rastagno explaining surface tension. Remember this story about density variation around the surface? This is mean field treatment of the surface. So how do you go here? You write Poisson equation. You assume that all concentrations are Boltzmann distributed in this mean field. You arrive in this badly nonlinear equation, which is called Poisson-Boltzmann equation, and I am very fast. The only thing that I will emphasize here in that it's called Poisson-Boltzmann equation, but don't believe that Poisson-Boltzmann collaborated to derive this, because Poisson died 4 years before Boltzmann was born. So there was no chance they could have collaborated on this. Okay, if you linearize this equation, you obtain the bi-Huckel equation, which if you consider field around point charge, this is your screened potential, exponentially screened potential. Most of the people may have seen it, but I went through this simple hand-waving argument to give you a feeling of what this whole story of screening means. Okay, so any questions? Yes.
I knew about the debye length before, but what I did not know is that it can be written as the product. It depends on both the concentration and on this fundamental length scale, which you call LV.
Absolutely.
So what is the interpretation? I don't understand. What is the interpretation of, again, why it depends on both concentration and this fundamental? The length scale comes from LV, comes from balancing KT with electrostatic potential.
Yes. So that means that indeed, physically, this means that the bi-screening length is controlled by concentration and KT. It's a balance of concentration and KT. How it is balanced is essentially through this Theorem length, which involves also dielectric constant of background neutral liquid. And it is very important that there is KT. Otherwise, you see, think about it from the units point of view. This C would have concentration, would have units of inverted volume. So if you want to have 1/2 power, you have to have a length from units point of view. And this length is this Theorem length. The Theorem length, I remind to you, is a very simple concept. It's the distance between two charges, elementary charges, that interact with the energy of KT. Okay?
What happens if the balance is smaller than the charge?
I actually erased a number of slides, including the slide about the applicability conditions of the bi-Huckel theory. The bi-Huckel theory is applicable, if you think about it, basically as long as the bi-screening length is longer than Theorem length. You can, one of the ways to think about it would be to say that it's longer than Theorem length. So in part, okay, so now I want to digress and tell you something about, this was pretty old, the bi-Huckel theory. And Huckel, by the way, when they derived it together, Huckel was a student of Peter Debye, and it was in 1923, almost exactly 100 years ago. So it's not quite over a century old ideas, but it's quite old. Now I want to tell you something very briefly, something from basically current literature. Another system which has no charges but exhibits similar physics. So imagine a colloid, which maybe enzyme or molecule, that catalyzes chemical reaction transforming A into B. And suppose in the infinity you have supply of A's and you take away B's. Then in steady state, there will be diffusion of A's inward and diffusions of B's outward, and you will have concentration that will go like 1/r. And 1/r should remind you something. This is fundamental solution of Laplace equation, and of course Laplace was supported by Napoleon, as I told you previous time. And Napoleon actually granted to him a house in the center of Paris, 5 minutes walk from the d'Orsay. So there is a plaque on this house, which there was Laplace, but the plaque does not say that fundamental solution is 1/r. I think it's they miss it. Okay, so there is 1/r, and if you imagine that there is another colloid some distance away here, It lives in the gradient of concentration, and because of diffusiophoresis, it feels a force which is proportional to 1 over r squared. So these colloids will now, or enzymes, will now feel force, which is like Coulomb force, although there are no charges, nothing like that. Moreover, if you imagine many colloids, then there is the Bi-Huckel screening effect, except it's tricky. It's a bit different. The physics is a bit different because what is being screened in the Bi-Huckel case is potential, essentially, electric field. What is being screened here is particles inside the volume. They effectively, like they have no charge. But I don't want to go very deeply there, but if anyone is interested, we can discuss it. It's a very beautiful, interesting thing, mostly invented by Ramin Galeshtanian a couple of years ago. Okay, let's go. Polyelectrolytes. There are many polyelectrolytes, and those are just a couple examples that I took from my own book because I have pictures of this easier found. Important part of this, to me, is that on every picture like this, I draw a counter ion to remind to you that this polymer chain is charged. There is minus sign, there is minus sign, but it is charged because, not because it's going to supply France with electricity, but because it dropped counter ions. Counter ions are somewhere not very far. DNA is, of course, the most famous polyelectrolyte, negative polyelectrolyte, and this is a picture. And many proteins are so-called polyampholites, which means that they have charges of both sign in their chains. Okay. So let's think. You guys are already well prepared. You can think about. Of course, your first thought would be to do Flory theory. Flory theory for a single chain. Okay, single chain Flory theory, you know how it works. You have to balance elastic energy with interactions, and interactions you cannot write as square of concentration. We learned already that. So your interaction will be Coulomb interaction. So it's charge squared, Bjorn radius divided by r, and so far I removed counter ions from this picture. I think that counter ions went somewhere. They just left. So it is a question where they left and how many of them are left. So if we have time, we'll go there. No screening, yes. No screening because there is no salt, because there are no counter ions. There is no chance to screen anything. It's just a set of charged monomers, and that's it. So no screening. So this is square of charge. F is a fraction of monomers that are charged. So you minimize this, you discover something like this, which is a beautiful thing. It means that your coil is not like this at all. It is something strongly elongated. The chain will, and this is precisely because this picture is already on the way to supply France with electricity for 100 years. It starts already supplying France. It cannot supply France, but definitely it can supply one polymer chain. Okay, so you can do it a little better since you know that this is elongated, this is like a cucumber, so you can do it a bit better by remembering that electrostatic energy of an elongated object has this logarithmic term, and you discover that it is indeed strongly stretched, and I don't want to go into this very much. the story is that it is stretched indeed. If there are no balancing ions, then repulsion force is very strong. So, of course, how can we go without blobs? We can reformulate this story in terms of blobs. We can imagine a piece of a chain whose electrostatic energy is just about kT. And electrostatic energy, how do we write it? Square of charge, Theorem length divided by the size of this blob. And here is your kBt. And now the relation between inside the blob, charges are not very important, play minor role, and so therefore the relation between the size and the number of monomers in the blob is either this or that, depending on whether your polymer lives in a good solvent or theta solvent with respect to non-Coulomb interaction. So this is an important thing. I have Coulomb interaction, but on top of it, I have, of course, everything else. All these van der Waals interactions between polymer and solvent and all of this is present. So the solvent may be theta solvent, maybe a good solvent, maybe anything else. So depending on this, you will have different relations. So you have two equations for two unknowns, the number of monomers in the blob and the size of the blob, and you go through the algebra, and I will not go through the algebra, but I encourage you to go through the algebra. And you discover that indeed, again, this picture reproduces the Flory result, that it is stretched. The length of the cucumber is linearly proportional to the number of these monomers, and you can do it now in good solvent or in theta solvent, and this is, so it's good. It's linearly proportional. There is no square root of n. It's linearly proportional to n. Because there are no counterbalancing charges. So you can, the only thing that counterbalance you is entropic elasticity, but it's far too weak against this force that is going to supply France for 100 years. France is a big country. Okay? Now you can ask me what happens if you place this into a poor solvent, and then you have to really consult Michael Rubinstein, who invented this, and this is a beautiful, super beautiful story, which I admire. So what happens is now you have competition between attractive forces that want because your chain is poor solvent with respect to non-Coulomb interactions. So these interactions want to collapse your chain, want to make a globule. And you have Coulomb forces that want you to stretch. How you balance it, it turns out that you balance it by making this necklace. So I suspect that he invented this when he wanted to give a nice birthday to his wife. But that was a beautiful idea, and indeed it works like this. So there are some simulation results and so on. I will not go into any details of it for the lack of time. So this is a slide that you have already seen, and then at that time you knew these three versions, and I told you I will return to this, and I did. So this is it. Okay, so any questions on this part? Yes? Why the radius of the electrostatic blob is not the biradius? There is no the biradius here. The biradius comes in because you have pluses and minuses. And pluses and minuses redistribute themselves to protect one another, to screen one another. If you have a positive charge, it is predominantly surrounded by negative charges, and vice versa. in this picture, I assumed, and this is not a very good assumption, but I assumed so far that even counter ions somehow went away. They went on vacation and they don't do their job. They went somewhere. They enjoy too much entropy. They just departed. No counter ions and no salt. So if, for instance, my polymer is positively charged, then there is no negatives around. So no debye screening, no screening, no debye screening, no debye, no Huckel. If we have salt, there will be separate slide. There will be separate slide. Okay. So now about polyamphalites. Polyamphalites, on the same level, polyamphalites are, you can imagine random polyamphalites, or you can, of course, imagine all sorts of sequences of pluses and minuses in this molecule. But the interesting thing is the most natural would be random polyamphalites. So here random polyamphalites you can imagine two versions of random polyamphalites. One is truly random that this chimpanzee will produce if it has a typewriter with only 2 buttons, plus and minus, it will boom, 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 boom. By the way, searching for this picture, I discovered that there is, I Googled monkey at a typewriter. So Google spit out a Wikipedia article which is called Infinite Monkey Theorem. It's quite amazing what our friends mathematicians are doing. There is a theorem that is called Infinite Monkey Theorem. I can tell you what this theorem is, quite amazing. This will be, of course, some sequence of n pluses and minuses, random. Alternatively, you can make a truly neutral polyamphilite, which means you take exactly 1/2 n pluses and exactly 1/2 n minuses, and then you reshuffle them randomly. But you guaranteed by construction that the charge of this system is 0. While in this case, of course, there will be some charge imbalance, typically. So how do we proceed in terms of Flory consideration for these two kinds? Yes?
What is the difference between the polyamphilite case and what we saw before? The charges are discretely placed?
No, the difference is that here you have sequence of pluses and minuses. Previously, we have either only pluses or only minuses. That's the difference between polyelectrolyte and polyamphilite. So polyelectrolyte in the field of biophysics would be RNA or DNA. It's purely negative. Pure repulsion, everything is repulsive. Protein is not like this. Proteins, typical, vast majority of proteins, they have positively charged residues and negatively charged residues. And depending on pH, you can actually control it. And for many proteins, there is an isoelectric point when it's neutral and has equal number of positives and negatives. Okay, so let's go. Wrong direction. Okay, so if you have truly random sequence of plus and minuses, you have this charge imbalance because monkey produced something not necessarily neutral for you. And then Flory theory will tell you that there is, of course, elastic balance, elastic free energy, elastic, how do you call it, free energy, entropic elasticity. And for some reason, B became A, but they are close in alphabet, so that's okay. And then there is this N, which comes from squaring this charge. And remember, for polyelectrolyte, it was N square here. And this is the difference between polyelectrolyte and polyampholyte. Inverse and LB. Yeah? Good. Very good. And then you discovered that this thing, it is, the power here is a bit bigger than n to 1/2. So it's stretched, not quite completely stretched, but it is stretched because of the excess charge. A random, because monkey is not a reliable producer of neutral polyampholyte, sorry. On the other hand, if you have truly neutral sequence of plus and minuses, then something beautiful happens. Because now, what happens is these plus and minuses, they attract each other. This thing actually forms a globule. And this globule inside, you can imagine that there are pluses and minuses. And this is already reminiscent of the pictures of salt and Debye screening lens, and Debye would love to see this picture inside the globule. There are pluses and minuses. It's neutral. And you know that pluses and minuses are able to arrange themselves such that their energy is negative. They have correlation energy, which is negative. They enjoy the company each other, and they are able to correlate themselves such that their energy is negative. So you have this negative contribution. This is our Coulomb energy, which is 1 kT per Debye screening lens. Debye screening lens is repeated here in different form. So F times N is the charge. So if you go, it is energy kT per Debye blob. And it is balanced by, let's say, for instance, two-body non-Coulomb repulsion, which is proportional to n squared. And you discovered that this goes now as n to the 1/3, which means it's a globule. And beautifully, by the way, previously, up to this point, I told you all counter ions, they are out of the picture. Here, I can say, okay, suppose there were counter ions. But since this molecule is neutral, it does not need counter ions. It's neutral already itself, so these counter ions are released away. So the gain of free energy that you obtain by releasing these counter ions is something that helps you to collapse your chain. Any questions on this subject? Well, if the chain is indeed, Michael is right, is in vast majority of cases when Michael says something, he is right. That's experimental observation, but it's only majority. So he says, if the chain, I will reformulate it. He says, if the chain is not very flexible and it has pluses and minuses, then it cannot really completely arrange pluses and minuses in proper way. This is true. This is true. So among the applicability conditions of this picture that I presented is the assumption that essentially pluses and minuses, there are not too many of these pluses and minuses along the chain such that pieces of chain between neighboring charges are sufficiently flexible. If they are sufficiently flexibly arranged, the sequence is not particularly important. But yes, there are tricky issues, and some sequences will, in some cases, they will form sort of a ladder in which long pieces of pluses will be paired with long pieces of minuses. So there are subtle conditions of applicability for this picture, but this is picture that has applicability conditions. It's not universally applicable always. Yes? How does solvent affect it? It does. For instance, here you remember that there is V times tau, and tau is precisely the solvent quality. So the solvent quality is right here. So it does affect it, because in this case what happens is it is the balance between electrostatic correlation energy between pluses and minuses that comfortably arrange in space and interact through self-consistent electrostatic field, and non-Coulomb regular exclude volume or related to solvent interactions that are happening here. They are non-Coulomb, they are proportional to square of the number of particles. This is pair interactions. This part depends on the solvent. This part, well, it a little bit depends on the solvent because there is epsilon, there is dielectric constant of the solvent, but mostly this part depends on the solvent quality. How do I derive this formula from this one? Yes, it depends on the solvent, but the main point is this n to the 1/3. It may not be, maybe it's a terminology question. By collapse, I do not necessarily mean that it is collapsed to dry volume. I don't mean that it became a black hole or anything like this. It is collapsed in the sense, the only strict meaning that I use for this word is the fact that the size of this object is proportional to n to the 1/3. The significance of this 1/3 power is that think about r cubed divided by n, which is the density of this object, right? Or rather maybe volume per particle, r cubed divided by n. This is some power of this quantity, and this is independent of chain length. So that means if you imagine your globule and you look at little piece inside, the density of this little piece is balanced by some forces inside this little piece. It's not balanced by the whole thing. Okay? Remember Frederick's lecture this morning? There is bulk of liquid in which density of liquid is balanced by liquid laws, and then there is separate issue of the surface. So this is exactly the statement that this is a droplet somehow balanced inside itself. In this sense, it is collapsed. Yes?
So there is an attractive term and there is a repulsive term. The repulsive term is d by electrostatic repulsion, right?
The repulsive term is this, and this is non-Coulomb interaction.
Non-Coulomb, d by screen.
No, it's non-Coulomb. Non-Coulomb means, let's say, excluded volume. Van der Waals forces, all of these things, all the stories that you learned in the previous week, all the stories of good solvent, bad solvent, all of this is not for charged particles. It's non-Coulomb interactions. Well, on the surface of things, yes, nothing electric about it. But a little deeper, you discover that, in fact, van der Waals forces are interaction between temporary electric dipoles with delay due to speed of light. It's not 1 over. It's 1 over R6, 1 over R something else. So it's some little pieces of Coulomb interaction.
And so the attractive part, where does that come
The attractive part is the correlation. This is Coulomb part. This is Coulomb part. This is just another way to write. Remember, I wrote that correlation energy per unit volume, it is kT divided by RD cubed. It is kT per debye blob. So this is another just algebraically different way to write it down. Because you see the bi-screening length is this. Yeah, and divided by R cube is concentration, F, N is charge, and so on. And then you have this LB, and then you just do what? You take this R cube, and you take KT divided by R cube, and this is your answer. See, it is...
It is a non-trivial 3/2 power, okay?
Yes, it is a non-trivial 3/2 power, and this is your non-trivial 3/2 power, because remember that the bi-screening length is concentration times Theorem length to the power minus 1/2. And this is non-trivial power minus 1/2 and non-trivial power 3, and this is all combined to give you this 3/2. This is a non-trivial power. I'm not necessarily saying that this is something trivial. Okay? So this was polyamphalite, the chain in which we have pluses and minuses. And by the way, when should I stop? I don't know. Another 20 minutes. Very wonderful. Okay. Of course, I will cover on the insignificant fraction of slides that I prepared, but that's okay. It's much better to discuss things that you are asking than cover more things. Okay, so there was this polyamphalite chain with complex sequence of pluses and minuses. Now let's do another object in which you have separately polyelectrolyte of pluses and separately polyelectrolyte of minuses. And I took this picture from Abhinaya Arunashalam. Sorry, Abhinaya, I do not master pronunciation of your name. She was kind enough to send her picture from the poster, and this is the name of her poster. And she studies, for some purpose, complexes of polyelectrolytes. And this is a huge field of, to which I do not make any justice. I just mention it as this answers the question why I use the word potpourri in the title of this lecture. So what happens if you mix negatively charged and positively charged things together? And suppose you do it at sufficiently low concentration. So your positive chain, suppose you have chains of the same length, same number of ions. So you have positive chain that has, I don't know, 1,000 charges, and negative chain that also have 1,000 charges. What will they do? Obviously, they will come together. It's very favorable. While they are each separate, they have to worry about their counterions, and we will maybe have time to talk about this counterion problem. But while they separate, each should worry about counterions. Each is surrounded somehow by counterions. Now, if they come together, this complex is neutral. Counterions say, hello, goodbye. We go enjoy our entropy. and you two big guys sit there. This sitting there means you have polyelectrolyte complex. Of course, in not very dilute solution, this complex will precipitate and form condensed phase. Dilute solution, just two of them will somehow form. Probably, if they are flexible enough and so on and so forth, they will form a globule of some sort. But counterions will go away. This is the gate to the entire new field, which, for instance, includes such object as DNA with proteins in chromatin. DNA is hugely negatively charged. How can you possibly pack DNA in the cell of your nucleus? The only way you do it is because it's not naked DNA, it's not naked negatively charged object. It's a complex with positively charged proteins. Most of these proteins form these so-called nucleosomes and so on. And this is a complex of positive and negative charges that allows you to live. So you should appreciate it. There are many interesting questions here. I told you what happens if two chains. I told you a little bit about what happens if two chains of the same charge come together and form a complex. But how about more realistic case when one of them is longer and has more charges than the other? For instance, if you have 1,000 charges positive chain, and you can make a complex, obviously, with two negatives 500 each. That's pretty obvious. Can you, but if you have 1,000 and two of negatives, 1,000 positives and two of negatives with 600 each, will you make something that overall has positive charge, or will you not? It's an interesting question. And here is a cartoon which shows that it's possible. It's interestingly possible to make a complex with imbalanced charge. It may be energetically favorable, surprisingly. And this is illustrated in this picture. So suppose you have this negatively charged object here. You can think that this is DNA. And it is presently neutralized by, let's say, positive B's. So everything is neutralized, everything is neutral and happy, and presently one more guy comes in. They were going for a boat trip, and this guy did not write his name in, or her name in the list for boat trip, and now he arrives to the boat and says, would you allow me in? And then it turns out that yes, they would allow it in by the following mechanism. Instead of, for simplicity, imagine that it has just 3 charges for this cartoon. So imagine that, so basically what you have to do is you have to vacate three vacancies, 3 places. So what you do is you ask 3 of your molecules to do some kink or something like this. Then of course, this charge and this charge and this charge are unhappy. So there is no magic. There were 3 charges in excess, and there are still 3 charges in excess here. But they were very close. 3 charges in excess were very close to one another. They were repelling strongly. There were very high energy, and now these 3 charges are much further apart. The repulsion energy is reduced. It's favorable.
So each of these is a polymer chain.
Sorry?
Each of these things is a polymer chain.
Yeah, each of these things is polymer chain of 3 monomers. It's a cartoon. Look.
Yeah, I understand. But so the black one with 3 charges just broke apart into 3 single. That's what you're saying?
No, nothing is, no bonds are broken. No bonds are broken. The whole thing is that this triplet, it does not lie flat like this. It extends one of his charges upward. This does the same. So they ask three volunteers to maybe, instead of going inside the boat, they are sitting like that on the side of the boat with one leg in the water.
So there is an energy cost, but it's curvature energy.
Yes, there is energy cost, of course, but still, this situation is better than this one. So it is an interesting question, how much of extra charge you can put there. But you can put extra charge. So when you think about complex of DNA with nucleosomes, it's not necessarily neutral. There might be charge imbalance one way or the other. Okay, and now I told you there will be the story of where counterions go, but really I suspect that I have about 5 minutes left or so. So, sorry guys, there is no chance. And the story is that when you, for a polymer, I will just tell you that for plane of charges, plane holds its ions, its charged plane holds its counterions within short distance. Charged sphere does not hold its ion. Ions in dilute system escape. Cylinder is an interesting intermediate case. Polymer is an interesting intermediate case. Because there is a competition between releasing ions to some distance requires this energy, and this is because the logarithmic dependence is because if you solve electrostatic problems in 2 dimensions, then the result of Laplace equation discovered 5 minutes walk from Musée d'Orsay due to the house presented by Napoleon. I wonder, by the way, if Emmanuel Macron presents a house in the center of Paris to somebody clever. Maybe there will be a similar discovery made. So this is logarithmic dependence for energy. But entropy also goes logarithmically. So whether counterions will be released to infinity or will not be released to infinity depends on coefficients. Which coefficient is better? This coefficient for entropy is basically KBT. This coefficient for energy is basically linear charge density. And the answer is beautiful. The answer is there is critical linear charge density, which is nothing else but one elementary charge by Theorem length. So if you have more charges than 1 per Theorem length, then your charges cannot escape to infinity. They are condensed back on the DNA. And in fact, DNA, for instance, double helical DNA has linear charge density, formally speaking, 4 times this critical. And so 3/4 of counterions for DNA has to be somewhere very close to the DNA. This, of course, will have lots of consequences. They condense. This will keep condensing. They keep condensing. I promise that it will stop at some point. Still condensing. When I prepared this slide, I even forgot how many times it. Okay, so If you go through this, you discover that this, of course, has consequences for Flory theory, this mining condensation, and so on and so forth. Then you discover what happens if you add salt, and then instead of completely straight chain, you start having chain which is somewhat stretched on short length scales, but then coils up on bigger length scales. There is controversy about it, and there is overlap concentration, and there is the story of semi-dilute solution and the concentration blobs, which Professor Brule told you about how to measure correlation length using scattering, and you can do scattering for polyelectrolytes, and you discovered that there is this unusual dependence on correlation length on concentration, and importantly, there is a blob concentration blob in which your chain is basically stretched, basically straight, just a single chain in Flory case. And there is osmotic pressure, and there is, I promised to you to talk about this, and I don't have time. And there are many other things, and mean field, and there is also the story of moving charge by the electric force and violation of Einstein relation. And okay, I will show to you the rest of the things that were here prepared. And okay, and the end of the story is that I probably showed you half of these slides, but this is useful because you asked questions less than I hoped you would. But okay, thank you.